This is lecture 9B, so the second half of lecture 9 talking about random variables. In lecture 9A we stopped off with this shorthand notation and we talked about the probability of an event and how it's usually written. Okay, so the probability of other events, such as the probability of events so that X ends up landing between A and B, can all be derived from the probability of capital X less than or equal to little x. So we can form all other probabilities by taking intersection, unions, complements, etc., etc. So for example, if we want to figure out what the probability of X being between A and B using only the probability of capital X less than or equal to B and capital X less than or equal to A, then what we want to do is we want to be able to write this interval A to B in terms of these two intervals, X less than B and X less than or equal to A. Okay, so how do we get this part here? Well, we can take X less than B, this is this part, and so, but what we want to do is we really want to cut off this part, right? So this blue line here is the complement of capital X less than A. So we can say that this interval, A to B, is the intersection between this set of numbers and this set of numbers. So this is the probability of capital X less than or equal to B intersected with the complement of capital X less than or equal to A. So now we have this. What do? So we have a probability of an intersection. How do we find the probability of an intersection? Well, if you recall, one of the things that we had derived earlier was what was the probability of two sets union together. Remember, the probability of two sets union together was equal to the probability of the set C plus the probability of the set D minus the probability of their intersection. Well, here's that intersection term. That's really what we want here, is how can I write the probability of the intersection? So just rewriting, you can get the probability of this intersection is equal to the probability of C plus the probability of D minus the probability of their union. Okay, so now we're going to use that up here to find a formula for the probability that X lies between little a and little b, using only the values probability of X less than or equal to B and probability of X less than or equal to A. Okay, so what we have is we have this first line is the exact same as up here. So what we can do is we can rewrite this intersection as the probability of our first set, so this is the probability of capital X less than B, plus the probability of our second set, this is the probability that capital X, the complement of capital X less than or equal to A, minus the probability of their union. Well, if you go back and look at the union here, so this is the union. What is the union of capital X being less than or equal to B and the complement capital X less than or equal to A? So let's look at the previous slide. What is the union between this blue and this dark blue? Well, it's the entire real line. So going back, we have the probability of this union, and this union is really just that capital X is on the real number line. Well, the probability that capital X is on the real number line is just 1. Remember, this is the probability X is less than or equal to B. We want to keep that. This is the probability of a complement, which is just 1 minus the probability of that set. So we simplify and we can get the probability that X is between A and B written as probability of capital X less than or equal to B minus probability of capital X is less than or equal to A. So we have something called a cumulative distribution function. Cumulative distribution function is basically exactly what we were talking about before. It's the probability that capital X is less than or equal to little x. This is called the cumulative distribution function. It's normally given the term capital F or capital F sub x. Lots of times that sub x is left out, and it's just understood that it is associated with the random variable capital X. So this cumulative distribution function, or c.d.f, is a non-decreasing right continuous. And basically, if you look at the probability as x is less than or equal to negative infinity, this should be 0. And as we go to positive infinity, this should be 1. If you have a discrete random variable, then you can associate the probability that your random variable takes on a particular value, because remember we're talking about discrete random variable, and this is what's called the probability mass function at x sub I. So this is the probability that your random variable is going to take on exactly the value x sub I, called the probability mass function at x sub I. So if we replace this x sub I with just x, then we get what's called the probability mass function of our random variable x. So this is denoted by p.m.f. So we've talked about c.d.f and p.m.f. And we're also going to introduce a p.d.f. So, and it's not PDF as in the document, that's a PDF document. So here we have, for discrete random variables, we can think about the probability that x takes on a certain value. If we randomize just any value, if we have an arbitrary value, this is called the probability mass function. Okay, so relating the c.d.f and our p.m.f for discrete random variable. So remember the c.d.f, what was the c.d.f? It's the probability that x is less, that our random variable, capital X, is less than or equal to some value, little x. So here we have that for x sub I in A, in our range, our f of xi, our probability mass function, has to sum up to being 1. So basically the probability that I'm going to take on a value in my range, if I sum all those probabilities up, it should be 1, because I will take on a value somewhere in my range of A. This is just our probability mass function at x sub I. So if I have, what's the probability that I'm going to be in B, which is a subset of A? Well, here I'm just looking at x in B of f of x. So, okay, so now how do we relate this to our cumulative distribution function? Well, we can say the cumulative distribution function of a random variable. Remember, this was probability that our capital X is less than or equal to little x. Remember, that's what this cumulative distribution function means. What is the probability that our random variable is going to take on the values less than or equal to little x? Well, if we have a discrete range, then really all we're doing is we want to sum up these probability mass functions at x sub I for all x sub I that are less than or equal to that value that we're looking at. So here we're going to sum over all the x sub I such that they're less than x. And here's our probability mass function at x sub I. Okay, so let's do an example of this. So let's consider our range of A being the numbers 1, 2, 3, 4, and 5. And let x be a discrete random variable such that the probability mass function at x sub I for any of those values is equal to 1/5. So basically there's equal probability of getting a 1, 2, 3, 4, or 5. So we're assuming a constant probability mass function for all. So notice that if I take the sum over this whole entire range A, I'm going to get 1, right? So that's the first thing to make sure that you have properly defined your probability mass function. Okay, so now what is our c.d.f? Our c.d.f is the probability that our value is less than or equal to little x. So if little x is less than 1, what is the probability that we're less than 1? Well, it's 0. What is the probability that little x is between 1 and 2? So what is the I should repeat that. What is the probability, what is our cumulative distribution f here what is the probability that our capital X is less than or equal to little x? So if little x lies between 1 and 2, what is the only value in our range here? What is the only value in our range so that capital X is less than or equal to, what is the only value in our range that x takes on? Here is just 1. What is the probability that we can get a 1? It's 1/5. So now here, if we look at little x being between 2 and 3, then really the only value in this that is in our range is 2. What's the probability that our function, our x, can take on a value less than 2? Well, it can take on a value less than 2 if I get a 2 or if I get a 1. So I add up these two. That's where I get the 2/5. What's the probability that our random variable can take on the value less than or equal to, in this case, it would be our 3, right? What's the probability that we could take on the value less than or equal to 3? Well, it's if I have a 1, a 2, or a 3. So this would be a probability of getting a 1 is 1/5, probability of getting a 2 is 1/5, probability of getting a 3 is 1/5. I add those all up, I get 3/5. So you can actually visualize this. Here is what our c.d.f looks like, and it's just a stair-step function. So what's the probability that I'm going to take on a value less than 1? It's 0. What's the probability I'm going to take on a value less than 2? It's 1/5 because I can only take on the 1. What's the probability that I'm going to take on a value less than 3? Well, it's the probability that I could have a 1 or a 2, so it's 2/5. So it's the stair-step function. And remember, after 5, what's the probability I could take on a 5 or anything above that? Well, it's 1 because I've now reached my entire set. Okay, so now let's talk about the probability density function. This is for continuous random variable. So we have the p.m.f when we're talking about discrete random variable. We need to generalize this for continuous random variable. So here, this is again is the probability. What is the, so capital F is our c.d.f. It's the probability that we're going to take on a value less than or equal to x. So we can think about summing up our values less than or equal to x, but remember when we're talking about continuous, then this translates to an integral. So if you remember calculus. So this little f, what are we summing up? This is called the probability density function. Here we're summing up our probability density function across all our values from negative infinity all the way up to x. So this little f is called a probability density function. The capital F is called our cumulative distribution function, or c.d.f. So if the c.d.f is integrable, then we get this relationship. So an example here, we're talking about let the space be of a continuous random variable be a is in 0 and 1, and the p.d.f be exactly f of x equal to 1. Then for x in a, what do we get? Well, we have a p.d.f of 1 here. So we plug in 1. What value do we get? Well, if x is less than 0, remember our range here, our range a can go between 0 and 1, so if x is less than 0, then we get a 0. If x is between 0 and 1 here, then we have our f is 1. So we integrate this and we just get x. And if we're out of our range, then we've already covered our entire range. So we get capital X. I mean, we just get probability of 1 for all x greater than or equal to 1. So this is what this c.d.f looks like. Okay, so just a little bit of information. The p.d.f of a continuous random variable can be used to compute the probability associated with an outcome or an event. So here, if we know the p.d.f, so we know our little f of x, and what's the probability that x is in a, you just integrate over all of a. And since a is our range, this has to be equal to 1. What's the probability that x is in b? Well, here, b is a subset of a, so you just integrate over just that subset. What's the probability that capital X is between A and B? Well, I can integrate from little a to little b, and I get my c.d.f of capital B minus my c.d.f of capital A. And again, here, if I'm just looking, I have this relationship between my probability that X is between A and B, not inclusive, is the same as my probability if I include one or both endpoints. Okay, so just a little bit of notation. We have a discrete random variable and we have the probability that X is equal to A, then this is the formula way of writing it. This is our probability mass function. And for discrete or continuous random variable, the probability that the capital X is less than or equal to little x is our cumulative distribution function, or c.d.f. So this is the end of week 2, the end of lecture 9, and you should be able to complete the assignment for week 2 now and take the quiz.